our next speaker is John Keeley, and he's a senior scientist with the U.S. Geologic Survey. And in his bio, he said he got to do sabbaticals in all 5 Mediterranean climates of the world, which just makes me jealous. So here's your clicker.
Thank you. Thank you, Lenya. And thank you, Craig. Nice introduction to winds, because that, of course, is what brings us here today, these big wind events. Of course, what is on everybody's mind are these October 2017 fires in the North Bay. Extreme offshore flow pushed these fires and produced the most catastrophic fires in California history in terms of losses of humans and property. But following that, just a couple months later, we had this big fire in Ventura, considered the largest fire in modern fire history, over 280,000 acres. And it burned at the same time there were a lot of other fires. It started, this is the Thomas fire here, started December 4th and burned all the way into January. Over 280,000 acres. There are a lot of other fires going on at the same time, had big impacts in terms of resources for fighting those fires. Just an outline of the Thomas fire started down here in Ventura County at Santa Paula and burned all the way up into Santa Barbara County. Now, at the time, we saw lots of reports in the media about how scientists, in particularly climatologists, were seeing that climate change was the basis of these wildfires, and in fact, even convinced our governor to describe, due to climate change, this is the new normal for our state. It may be the new normal for the state, but I think we have a ways to go before we can say to what extent climate change might have impacted on these events. One of the common proclamations in the news outlet with the Thomas fire from December 2017 was December fires are simply unheard of in Southern California, and so this had to be something new related to climate change. But in fact, going back to the early 1900s up to more recent years, we've had substantial sized fires in December. So December is not totally unique. It's not the common time for these big fires, but it certainly is something that we have seen in the past. One of the factors that some people pointed out that drove these big fires were the temperature anomalies at the time of the fire. And what these graphs show is this is temperature anomaly going back from 1990 to 2020 or 2017. And the zero line here is the mean temperature, and anything above zero means that year was warmer than the average, and anything below, it means it was cooler than the average. And what we can see if we look at, this is for winter, spring, summer, and autumn. Winter actually in Southern California was cooler in 2017 than the long-term average. But when we get to like spring and summer and autumn, it was definitely warmer, 1 to 2 degrees centigrade warmer during those seasons than the long-term average. But the thing to note here is the high temperatures in December were not any different than about 6 other years in the last decade. So we've had warm autumns without having large fire events. So it's a little hard to say to what extent that warming impacted our fires. Now, one of the things that's important about looking at climate and fire is recognizing what season you're talking about. Very often we see discussions of climate change and it talks about annual climates, but that's really not enough. We need to be looking at seasons because as these projections show, winter projections going out to 2060 show much greater changes in temperatures in the high latitudes in the northern hemisphere than summer. Summer has very different projections. So it's important to think about, if we're talking about future climate change, are we talking about what we forecast for the winter, or spring or summer or fall. And so that's an important parameter to focus on. And this is work that Alex Seifert and I have been working on for a few years, where we've tried to look at winter, spring, summer, and fall temperatures over the historical record of fires in the state. And we have good records from CAL FIRE protected lands, those are the brown areas, and the green being U.S. Forest Service lands in the state. We have records going back about 100 years for both of those agencies. What we did is we took the annual variation in temperatures, and this is just an illustration of annual temperature in the winter for a station near where I live, Ash Mountain. And you can see from year to year, the temperature changes quite a bit in winter, spring, summer, and fall. We took that annual variation and we asked, to what extent did the temperature in those seasons in that year impact the amount of area burned, to try and get an idea of how closely do fires track changes in temperature from year to year. This is just an illustration, and I'll just pick out a few key points here. I'm not going to go into this in a lot of detail, but what we did is we broke the state down into 5 climate divisions: North Coast here, the North Interior, Sierra Nevada, Central Coast, and Southern California. And then we looked at the temperature in a given year for winter, spring, summer, and fall versus the amount of area burned. And just a couple key things I'll point out. One is it doesn't matter what the temperature is like in the winter. It had no impact in any of our regions on area burned. And the same with autumn temperatures. So winter and autumn temperatures are not really critical. What is critical is spring temperatures in particular and summer temperatures, and most particularly in those areas from the Sierra Nevada northward. Central Coast and Southern Coast, these areas here, we have no significant relationship between what the temperature is in a given year and how much area burns. So it depends on what season you're looking at, what the temperatures are doing, and what part of the state you're looking at. Now, another important thing to note is in our 5 climate divisions, we saw no relationship between temperature in the winter and temperature or area burn. But if you take the whole state and you look at those relationships, this is winter, spring, summer, and fall. If you take the whole state of California, we do see significant relationships. And the reason we see them for the whole state is because we're mixing spatial and temporal variation. But when we look within a single climate division, we don't see any relationship in those 2 seasons, winter and autumn. Now, let me just describe the 2 extremes that we see in the state with respect to climate and fire. And they're probably well illustrated by looking at the Sierra Nevada, mostly dominated by coniferous forests, versus the South Coast region, mostly dominated by shrublands. And in general, what we see is that in the Sierra Nevada, there's strong relationships between temperature and amount of area burned in spring and summer. We also see relationships with precipitation. As precipitation goes up, the amount of area goes down in the Sierra Nevada. But when we look at someplace like Southern California, we don't see any relationship at all. It doesn't matter what the climate's doing in a particular year. It doesn't have a strong impact on area burn. And we think primarily the reason is in some parts of the state, like the southern part of the state, it's hot enough and it's dry enough every single year to produce a large fire event. So it doesn't really matter what the temperatures are doing. And this is illustrated here. This is the summer temperatures in the Sierra Nevada, and at the highest temperatures, average seasonal temperatures recorded 19 degrees centigrade, we see the highest area burn. In Southern California, the lowest summer temperatures we get are 19 degrees centigrade. So it's always hot enough and dry enough in that part of the state, apparently, to burn. Now, if we're going to look at fire and climate, we got to look at more than just a single parameter like average temperature or precipitation. And so we've done multivariate models, and we find that a couple interesting things. One is we can explain about half the variation from year to year in area burn in the Sierra Nevada based on climate. But in the southern part of the state, we can't come up with nearly as good a model. The other thing to note is if you break the record down into the first 50 years of record versus the last 50 years, the climate models change. And in the first half of the century, area burned was driven by the amount of precipitation in spring and summer. Now it's driven by temperature in the spring and summer. And the important thing about that is we're making forecasts far into the future. We have no clue as to whether or not these climate models are going to stay constant through time. And this certainly illustrates they can change dramatically just in the last 100 years. And what's interesting is they illustrate how very different drivers seem to have driven different peaks. This is the area burned in the Sierra Nevada by decade from 1910 up to the present. And we had a peak in 1920, and that peak area coincided with relatively low temperatures, but also low precipitation. If you look at the peaks we're seeing today, they're associated with very high temperatures and variable precipitation. So what's important to understand is that over time, the relationship of climate and fire is going to change. In the southern part of the state, we have relatively little relationship with climate. The only strong model we can get, and that only accounts for 25% of our variation, is prior year precipitation. And what's important about prior year precipitation is it produces grass growth, and grass growth leads to high fuel volumes the following year. And what's interesting, though, is prior year precipitation is really only important in the last 50 years. The prior 40 years here, we had no relationship at all. We think that's primarily due to the fact in the southern part of the state, we've seen massive type conversion of native shrublands to grasslands in the last 70 years. And so now this is reflecting more type conversion. Now, let me just focus on something other than climate, because there's obviously a lot more going on we haven't accounted for. We can only explain at best half the variation from year to year in area burn if we look just at climate. What about these other factors? Weather, which of course is something that has captured all our attention. As Craig pointed out, the weather patterns that drive these big fire events that we get in the autumn are due to this pressure system, high pressure in the interior, low pressure off the coast. And in Southern California, these are called Santa Ana winds. And I guess Southern Californians aren't as creative as Northern Californians because they call them Santa Anas no matter where you go in Southern California. They peak in November, but there's still lots of Santa Ana winds event in December as well, but they're autumn events. You can get Santa Ana winds in the spring. Usually it's too moist, though, to get a fire. Now, this is a description of all the mega fires that we've seen in Central and Southern California historically. We have 10 of them that we can recognize that are over 100,000 acres. Going back to one we've reconstructed from newspaper reports on the size of the Thomas Fire. The ones in red indicate they burned during Santa Ana events. And there's a couple things to note here. One is we've had 10 historically, but 6 of those have occurred just within the last couple decades. So this is perhaps an illustration of this new normal. The other thing to point out is Santa Ana days and what separated this huge Thomas Fire from all the rest. There were 10 days of Santa Ana winds. We've never seen that in the past. The highest number of Santa Ana wind days during a fire was the Matilaha fire from 1932. We had 5 days of Santa Ana winds. Typically, we have much less than that. So that's one of the things that sets this fire apart and perhaps is a factor in why it became so large. Now, the other important question to address is Why did we get this 10 days of Santa Ana wind events? Was this a freak event, or maybe this was some climate phenomenon that is perhaps tied to anthropogenic climate change? And this is interesting. December 4th, the day the Thomas Fire began, there was this blog under something described as Insights into the Ridiculously Resilient Ridge. And it refers to a pressure system off the coast here that off the coast of California that set up. And the prediction at the time was that this ridge was something that was likely to happen or persist for a couple weeks. And that very likely is one of the reasons we had a 10-day Santa Ana event. The big question is this something that is a result of anthropogenic climate change producing changes in this ridge? Or is this just a freak event? We could ask the same thing about the Tubbs Fire. This is, the red here shows the outline of the, I can't even read it from here. I think the red is the Hanley Fire from '64, and the black is the Tubbs Fire from 2010. It doesn't matter because they're both pretty much overlapped on each other. We've heard a fair bit about the Hanley Fire, the Tubbs Fire. One of the things that's interesting, though, is Dan Cahan at Scripps has recreated pressure systems during these two fire events, and there were big differences in the degree of the pressure cell that's set up during the Tubbs Fire compared to the Hanley Fire. And so part of the driver of the difference in these fires may have been due to differences in the intensity of those wind events. Another question is this difference a reflection of anthropogenic climate change? The answer is we simply don't know. It could just be a freak event, and this is an illustration of a freak event, courtesy of Hal Mooney, sent me this figure. This is something known as the Great Bakersfield Dust Storm of 1977. And you can just imagine if you were driving down the Grapevine during this event and you saw this wall of 1,000 feet or more of dust, it would have been a pretty dramatic event. This was clearly a freak event, and these other things we're seeing now may just be freak events as well. Now let's look at long-term drought. Long-term drought almost certainly is a driver in fire events. If we look at these 10 major fires in the southern part of the state, and we look at the months of drought prior to the fire, normally we get about 6 months of drought every summer and autumn. This is the number of months prior to the fire event that was below 0 Palmer Drought Severity Index. In other words, were drought months. And one of the things we notice is almost all these big fire events are associated with a longer than normal antecedent drought. The two that are most spectacular are the two biggest ones, the Cedar Fire, 54 months of drought prior to the Cedar Fire. The Thomas Fire, 53 of the 72 months prior to that fire were drought. They weren't contiguous because we did have some wetter conditions in 2017. But if you go back all the way to 2012, which is right here, and this is the anomaly for precipitation. In Southern California, coastal Southern California, we had a severe drought that began in 2012, continued 2013, 2014. Now, much of the state, that drought ended, but it didn't end in Southern California, and we had a couple more years of severe drought. And so that is something that we find correlated with really big fire events, is very long antecedent drought. And this is just an illustration of how it depends on the season, how bad the drought was. Certainly last winter in Southern California, it was not a drought, but it was a drought in the other seasons of the year. Now, very often we think of the primary role of drought when it comes to fire as driving fuel moisture. But it's in these Santa Ana wind-driven fires, that may not be a critical issue, because normally this black line here represents the long-term average in fuel moisture, and this is autumn here, here's December out here. Normally, it's going to be very low fuel moisture in an average year, And 2018 certainly was lower than the average, but it still was not a huge difference between the long-term average and the fuel moisture in 2017. But what we do think happens when we have these long-term droughts, things like this. This is a view from my back porch on Case Mountain outside of Sequoia National Park. These are all dead ponderosa here resulting from this severe drought. So we've had a lot of tree dieback throughout the state, and we've heard that mentioned. And just to give you an illustration, the red here indicates really severe tree dieback in the state, mostly in the Sierra Nevada. One thing to note, there was not a huge amount of dieback associated with those areas that burned in the North Bay. So that may not have been a big factor in those fires. Now, if we look at the Thomas fire, if you go into the Santa Monica Mountains just south here, you can see lots of evidence today of the impact of that drought on dieback. These are all shrubs that have died back. All that gray are dead shrubs. We've had massive shrub dieback in the Santa Monica Mountains due to this long-term drought. And we think that this long-term drought may have been a factor in driving the size of this Thomas fire event. And the idea first came about from a discussion I had with Rich Hawkins. He was the Forest Service FMO on the Cedar Fire in 2003. And when I asked him why that fire got so big, he said every ember he saw blow downwind started a spot fire. And it's very likely that that 54 months of drought prior to the fire produced dieback that increased the ignitability of embers. Now let's look at ignitions, another important factor to be focusing on. The ignitions in the Southern California events are probably an important determinant of how much area burns, but but we often think of wind as being the primary factor. What this shows is the number of Santa Ana wind days every year for about a 30-year span. And what we've done is we've done a correlation between number of Santa Ana wind days and amount of area burned, and we get a correlation of 0. There's no relationship between number of Santa Ana days and area burned, and that's primarily because area burned is a function of the timing of an ignition when there's a Santa Ana wind event in a particular year, and it doesn't happen every year. Now, we've been looking, Alex and I have a paper now that is in review. We've been looking at changes in ignition patterns over the state, and it's a lot more interesting than I thought it was going to be. The red here indicates CAL FIRE protected lands. The green indicates Forest Service lands. This is the North Coast, North Interior, Sierra Nevada, Central Coast, and Southern California. And it wasn't too surprising that we saw an increase in ignitions in the first part of the 20th century, but what we didn't expect to see was a sharp decline in ignitions over the last 30 years. And almost certainly a big part of that has to do with fire prevention methods that have been put in place, as well as a lot of other methods that have been focused on trying to reduce ignitions. But one of the things that's fascinating is not all types of ignitions are changing, and this is just an illustration. This is arson fires on CAL FIRE lands in the north and in the south. They've been declining pretty sharply in the last 30 years. Same with debris burning or smoking fires. But there are other things like power lines. Power lines, in fact, power line fires have been going up, and in both the north and the south. They haven't been going up in the south, but they haven't been going down, that's for sure. And if we look at the area burned, we see a similar pattern. Arson fires, the area burned has been going down. Power lines, there's no change. So there's some things that we're being very effective at reducing when it comes to ignition sources. Power line ignited fires is not one of them. Lastly, let's just say a few words about land management and fuels. This is an illustration of the fire history of the area burned by the Thomas fire in Ventura County. The hatch marks indicate area burned, and the different colors area indicate the prior fire history. One of the things to note is that a lot of the area that burned in the Thomas Fire was not extremely old, maybe 20 or 30 years of age. When it comes to chaparral, that's not extremely old because that's close to the bottom threshold of what that vegetation can tolerate. The other thing to note is these dark blue areas indicate areas that there were prescribed burns done prior to the fire, within the prior decade of the fire. And it's important to realize that these prescription burns, this represents about 1,000 acres of prescribed burns, they may be effective under some conditions, but if you're going to have one of these powerful wind-driven events, the wind just blows right over them. And it obviously had no impact on the spread of that, or no obvious impact on the spread of that fire. The last thing I'll just point to are mudslides following the Thomas Fire. This was a tragic event where debris and mud came down these really steep ravines and literally buried houses. You can find houses where the roof is all that's still surviving. Primarily it was 3 drainages, the Montecito, the San Isidro, and the Buena Vista. These are really steep drainages, and that almost certainly had some impact on how devastating these events were, but it's also possible fire history had something to do with it. This is the fire history map up a little closer. Here are the drainages where the really catastrophic events occurred, and one of the things to note is that a lot of the area, significant amount of this area was 60 to 90, some of it even over 100 years of age. And so it's possible that as this vegetation has aged, it's accumulated more and more sediment, and that may have been a contributing factor, but that's just speculation at this point. So I'll just summarize what we can say about these 2017 fires. They certainly caught our attention. They made scientists recognize there's a lot that we haven't told managers about how to deal with these events. They've been the most catastrophic and largest in modern history. We clearly know that extreme wind events were part of this. We know that multi-year prior drought had the potential for making these fires worse. The question that is still a big unknown is how much anthropogenic climate change might have impacted this. It's possible that the higher than normal autumn temperatures might have played a role. We don't have any strong reason for believing that simply because we've had warm autumns before. But it does raise the question as whether the extreme winds that we saw in 2017, worse than we've seen in previous years, is perhaps something driven by climate change, anthropogenic climate change, or maybe just freak events. You'll just have to stay tuned. Thank you.
So we can take a direct question for John here, and then with Craig, would you come up? John and Craig, we're going to kind of do a discussion session with just you two guys for about 20 minutes. And so we're going to go with the roving microphones. I would ask, please, that let's focus on trying to get some new people. We obviously have a certain number of really engaged people who aren't afraid of the microphones. Please don't be afraid. Anyway, so you ready? You want to ask a question directly of John, or is this to the two?
Yes, directly of John.
Fantastic. Go for it. Okay.
This is the stand-up question.
Thank you, John, for your presentation, and very powerful. In terms of beetle kill trees, the view outside of from outside of your window, the photo you showed, I was wondering if you could comment on Sarah Hart's study, 2015, I think, where she summarized 12 years of data of fire across the western United States, superimposing beetle kill forests and burned area, and she found no relation between the beetle kill forest and burn area, and it seemed like there was, the beetle, once the red stage is done and its gray stage, it appears that doesn't have much of a relationship with the rate of fire spread.
Yeah, it doesn't appear that, at least in the Sierran forests that have been looked at, that beetle kill was the primary driver, and that severe drought was what induced that mortality. But one of the things you have to realize is we've perturbed Sierra Nevada forests a lot. And in the last 100 years, we've eliminated fire in many of these forests. And before climate change was invented, what fire scientists warned us about is the trees are getting very dense, very thick. We're way out of whack with the long-term norm. And it's possible that that mortality was a result of killing trees in an overstocked forest. And maybe if fire had been burning, we wouldn't have seen that mortality. That's just speculation. In terms of the role that they're going to have on fire, I think that changes over time. I think Scott Stevens probably would have a lot to say about that. He's just written an article talking about that very question and the potential role it will have on fire. Just very briefly, it'll change over time. Initially, these trees can be much more flammable because of the fine fuels. Once they drop those fine fuels, things could be very different, but maybe we can get Scott to talk about that at some time.